everyone, my name is Salma Lira, and this summer I focused on analyzing the correlation between air quality and radiation levels. We did this because there is a worsening of air quality in urban environments such as the San Francisco Bay Area. As we can see here on this pie chart, the dose of radiation that the U.S. residents get, 55% comes from radon, which is just a natural element that's radioactive in our environment. And the other, there's other percentages that just come from natural sources. So 82% of the average U.S. citizen's exposure to radiation does come from natural sources. So we wanted to collect data to see how this affects different things. So we have two major devices components. So here on the left, this is a Raspberry Pi, and that's what our detector has. And then we have a radiation watch dosimeter on the right, which is just a Geiger counter. This is the way that it collects the radiation levels, is by the Geiger counter. So then we have the network device. It includes a weatherproof case with a viewing screen on top. So there's just a clear screen on the top there. And it has a custom-made mounting structure, a dosimeter, and environmental sensors, in a Raspberry Pi again. Remember, the Raspberry Pi is this. These sensors are then placed in multiple parts throughout the San Francisco Bay Area and other places of interest. The sensors collect that data and then is sent directly to UC Berkeley's RadWatch network, which is available to the public in real time. We used a programming script to analyze any correlation between ionizing radiation levels and different environmental factors, such as humidity, rainfall, temperature, and air quality. For this project, I focused on air quality, and more specifically, I focused on PM 2.5, which means that we are looking at particulate matter in air with a size of 2.5 micrometers in diameter. So that's the particles in the air that's smaller than dust and pollen. We averaged the data over 1 hour to reduce any random variability. And as we can see here, this is a AQI chart. This is how we measure air quality index. So we have these values of index from 0 to 50, it's good air quality, 51 to 100, it's moderate air quality, 101 to 150 is unhealthy. And so this translates to like PM 2.5 concentration. So how much 2.5 is there when there's good air quality, when there's moderate air quality, etc. So the first things we saw when we looked at our results is we looked at a very low sensitive detector that didn't give us much correlation here. There wasn't any significant correlation of PM 2.5 and counts per minute, which is the CPM, which is the way we measure radiation. Our p-value was very high for this particular one. So then we moved on to more sensitive sensors, in which we looked at times where there was fires to see if there's any correlation, because when there's fires, there's worse air quality. So we wanted to see if there was any correlation between the amount of PM 2.5 and the counts per minute. So we see between November 3rd and November 19th, there were fires in the area, and that worsened the amount of particulate matter of 2.5. So then when we graph that to compare it to counts per minute, we do see a clear correlation here. And as we can see on the table here, for Echeverry Roof, which is one of the places in San Francisco Bay Area where we focused on, our p-value was really, really low, which tells us that the probability value of this being a random correlation is pretty much non-existent, so it's tiny. And then it's the same for Pine Wood. It's also really small for Pine Wood, which is a place near Palo Alto. We also see a really low p-value, which also tells us that this correlation here is not random. And then but because we are using our own detectors and our own sensors to do this data, we wanted to check a third-party sensor using Purple Air, which is an app that measures how much about like the air quality in our air. We wanted to see this for consistency. So when we looked at the Purple Air data, we did a study to understand if there were any biases in our sensors that might distort any correlation in our graphs. However, we did notice that even though that there wasn't a perfect agreement between like these time series graphs here and the Purple Air data, the daily average mean difference was 1.45, which tells us that there is only about 1% to 5% discrepancy with our air quality measurements. This means that it weakens our correlation by only 1% to 5%, which is not much given that our R-squared value is 30%, and then for PM 2.5, and for pine wood it was 50%. So it only weakens our correlation by very, very little. So this means that this uncertainty increases the random fluctuations in the particulate matter levels, thus weakening the proportion of variance in radiation that could then be attributed to changes in air quality, but not enough change to reduce the statistical significance of the observed correlation from these graphs. We'd focus on times when there were fires because during those times there are higher particulate matter in the atmosphere. Since there are natural radioactive elements in the air during these times when there is a higher AQI, there is also a higher fraction of the particulate matter in the air that is radioactive, because that's just how math works. It was important to look at when there were no fires in the area to see if there were any correlations at all. And then when we did this, we saw that there was a weak correlation because there's always background radiation that is just constant. So the AQI during these times was 0 to 54, which means it was very good air quality to moderate air quality, which didn't change the counts per minute. And then the high p-value of 0.87 suggested that any correlation there was random and it wasn't attributed to anything. And then again, this is because there's just constant naturally occurring radioactive matter in our atmosphere. So when we looked at the correlation of different environmental factors and radon levels, we could see that when there was a higher air quality index in AQI, there was also a higher amount of counts per minute (CPM). So this alludes to the fact that when there is more particulate matter in the atmosphere, there is a higher amount of radiation. This isn't simply because the amount of air quality increases the radiation levels, however. This is because of the fact that when there is more particulate matter in the atmosphere, there is also a higher fraction of radioactive matter in the environment. So even though we've collected very significant, important data here, we want to continue to collect data from a more sensitive sensor, which is non-operational for now. So first we would have to fix that sensor. Then that sensor would collect data, and we would generate an energy spectra that will then be used to determine which isotopes specifically are contributing to increases in radiation levels as air particulate concentration increases. So we want to look for specific isotopes such as radon daughters or potassium and other natural elements to understand the relationship between the sources increases particulates and the radioactive materials leading to increases in radiation. So here are my references that I used. Purple Air is one of the big ones that I used. And I'd like to thank Dr. Ali Hanks, who guided me through my data processing and analysis for giving me the opportunity to work alongside her this summer, and to Richie Wu, who allowed me to use his Purple Air data, and then to my program coordinator for helping me with content planning for science classrooms. Thank you. Bye.